qubits with the idea that to make an active qubit and make quantum communication and quantum computers, quantum sensors, that you don't have to have a dilution refrigerator is extremely attractive and has really booted up a new line of research. The angle now, which we'll be telling you about, is how you can actually engineer these qubits into a system that's working where they talk to the outside world via photons and find ways to make them talk with each other and develop a technology that's really based on this. Dirk got his undergraduate degree from Caltech, as I did when I was young, and also then moved to Stanford and then Columbia and MIT. Dirk.
Thanks so much for the introduction, Bob, and for your leadership of the center altogether. So it's great to be here today. Put this thing on first. So yeah, so I'm going to talk a bit about some of the work in my group and with our collaborators on building devices and systems for quantum communication and modular quantum computers. But I want to start this off with this slide and just sort of ask the audience, does anybody recognize that machine? No? Harvard? Close. I've heard Pennsylvania before, which is good also. Penn State. Anybody? No? Oh, okay. That is the Mark II, is the Colossus Mark II. So I happen to know what it is because I actually got to go to Bletchley Park a couple of years ago in the UK, where this is on exhibit. If you make it over near London, you should definitely try to make a day trip out of it. It's pretty fascinating. So this is the device that helped change the course of World War II. And what you see here is intercepts from German communications being fed by this sort of punch card. There's actually this sort of long tape into this computer, and ultimately by sending enough intercepted messages through, it was possible to break a device that people thought, for decades would be unbreakable, and that is the Enigma machine that was used by Germany for a couple of decades. And basically, people assumed that this machine, which takes an input and then scrambles an input, a bunch of letters, by some combination of wheels that change the connectivity of wires inside of this machine, it was thought that this machine would be unbreakable, but they never had a security proof. It just seemed extremely hard, but there was no proof that it actually was impossible to break it. And so this changed history. And the transistor that was the switch that was used inside of this Colossus is shown here, and it consists of a thermionic vacuum tube that you can see here. And that device, of course, is clunky. It's about this big. You see it in real life. So then, of course, in 1947, figured out how to do this using germanium, and then in silicon. And once that was done, and once they had a good control of individual transistors, they could scale it up, and now every one of us has several billions of transistors in our pockets. And that, of course, has been possible by making these transistors smaller and smaller. So for a long time, we saw Moore's law scaling, where every 18 months or so, the density of transistors on a chip was cut in half, was doubled. And so, and that, has led us to the point where nowadays you can basically no longer scale by that same law. And it turns out leakage resistance for very small transistors comes to be a major problem. But even if that wasn't the issue, ultimately you'd run into a wall, because eventually you're going to have to deal with the size scale of atoms. If you just if you just projected this outward by 2020 or so, if we did follow Moore's law, we would deal with nanometer size, feature sizes. And then things, of course, become very different. At nanometer scales, our transistors don't behave properly anymore. Electrons don't stay in our channels. They start to tunnel. Of course, you can make use of that. And so, if you look at it like, as a blessing rather than a curse, you could start thinking about how can we actually make use of these quantum effects, and that has led to a number of quantum technologies that are now emerging. And these, just sort of to recap a bit, are based on, I think, two primary principles. First, the superposition principle, where whereas a classical register of 2 bits, for example, could be only in one state, like 0, 1, in a quantum world, it can be in all 4 possible states at the same time. And that number of states for the superposition becomes exponentially large with the number of quantum bits that are part of it. And just, as an example, if you wanted to simulate on a classical computer something like 60 quantum bits, and this would be just, let's say, electron spins, are they pointing upward or are they pointing downward, and not taking into account their motion, their angular moment, their momentum, their position, and so forth, just that would require something like 100 million terabytes of data. If you have if you just wanted to write down an arbitrary state of 60 qubits, 100 million terabytes. And I have a friend who now works at a Google data center, so he can't tell me exactly how much storage they have, but he says it's on that order. So basically, just to store 60 two-level systems, you need the storage capacity of a Google data center, right? Let alone, let's say, solve it in some way. Like, if you want to have particular couplings between these qubits, for example, to represent a molecule or so, and try to understand what are the electronic levels of that molecule, it's impossible, because at the base, these quantum simulations scale so badly. And that, of course, is the idea of quantum simulation. Can we somehow take a system that we have good control over in the laboratory and map interesting physics onto that quantum system, and then predict something about a molecule, or perhaps about complicated many-body quantum materials? And that, of course, is a big focus here. And if you get more sophisticated operations between perform gates, but running algorithms for optimization or for things like mechanics, that's a bit off. You have, if I give you systems nowadays, sequence of the proven separated by some distance, and they wanna that is not known to also this and one state, which is a super, will get the same result. This architecture somehow build. Dropper can listen in. And serve as a cryptographic key for one-time pad encryption, and that one-time pad encryption is unconditionally secure. Okay, so the point is, some decades ago, even today, you look at the protocols used for cryptography, public key encryption has actually no figured out this algorithm as we were. But they would also quantum networks. Here at Harvard, number of problems, right? Schemes are low, nighttime condition, background from sunlight, and so forth. So what I want to talk about here is what are the next steps in QKD first, and then other schemes, quantum network schemes that would allow us to distribute entanglement over even greater distances. And so just that, I should say, this was possible through a hardworking group at here at MIT in my group, and through close collaborations with a number of collaborators, including with people here at Harvard. Okay, so let me launch into it. So we've been working over the last 4 or so years on implementing a testbed for testing out these quantum key distribution protocols in the ground as a field test. It's one thing to do it in the laboratory. It's another to actually do it in the field, where you have to contend with temperature fluctuations, cars driving over highways that maybe maybe vibrate your fiber, and all these things. So, so we have now a fiber, a dual-stranded dark fiber that operates at 1.5 micron, it's telecom fiber, SMF28, between MIT Lincoln Laboratory in Lexington, Massachusetts, and the main campus of MIT. And it also extends to Harvard, actually, going to the group of Misha Lukin, and we're currently working on extending it to Marco Lonkar's group as part of the SICM. And actually, it also extends further to Raytheon BBN. So it's a decent-sized network to try out some things. And one of the protocols that we tried out, and this is currently still our record, is we developed a new kind of quantum key distribution protocol where, rather than using binary encoding, is it a 0 or 1, we used high-dimensional encoding, where the alphabet was consisting of the position and time of a photon. And here you can make large alphabets of up to 1,000 possible states of one photon in these time bins. And the benefit here is that every photon that you detect can tell you more than one bit of information if it's equally probable that this photon will arrive at any 1,000 of these possible states in time, then you get, the amount of information from that is just the entropy, if you like, of 1,000 equally probable states, and that's log base 2 of 1,000, or 10 bits of information. And that scheme allowed us to push a bit the key rate. And just to give you sort of an idea, like nowadays we're able to produce, and that's in this paper, we're able to produce this, this cryptographically secure key at a rate of about just a little bit over a megabit per second in a honest-to-goodness telecom, fiber, metropolitan, it has all kinds of splices. It goes through the AT&T distribution hub. So, it has all kinds of imperfections, but nonetheless, over this deployed fiber, we get sort of a megabit per second key rate. Now, if you are Comcast in my area, at 1 megabit per second, you say, okay, I'm done. Comcast is pretty bad in my area. But we want to go faster than that. And so we're looking at how, what are some methods that we could improve on this. And so one of the ways that you could do that is to not only run over one channel, you do what the telecom companies do, you go over many spectral channels at the same time. And so you could make a rack and just replicate the instruments that we used in this other experiment, or that other people around the world use, and just build a big rack and have one transmitter per channel, per spectral channel. But that becomes expensive and really unwieldy. So some time ago, and also I should say, when you buy telecom equipment, it's not normally sufficient. It's not normally good enough for QKD. Some of the timing is not good enough, and the modulation depth on/off, for example, the extinction isn't good enough. So you kind of have to develop either your own bulk hardware, or perhaps you use integrated optics. And we went a couple of years ago with an integrated optics approach, where the idea is that you can now go out and pay a company such as AIM Photonics or a number of other foundries for integrated optics, some amount of money per square millimeter, and they will make for you this amazingly good integrated optical components. Just as an example, here's, they do this on 30 centimeter wafers, so large scale. That means that the costs of this fabrication are distributed amongst many users using multi-project wafer runs, like Moses for electronics. And you can pack a lot of stuff on there. So for example, in a couple of millimeters square, we can include now tens of, we can have up to 50 channels or so, where each has a pretty good modulator on the transmitter. And the devices can be engineered so that they give us the right contrast and other things that we need for QKD. So let me just show you one early one. This is still a single channel. What you see here is a transmitter for polarization encoded QKD. So this is the first form of QKD that was actually proposed. And what you need to do is you need to send from Alice to Bob a 1, which is polarization, let's say vertical, or a 0, which is polarization horizontal, 1 or 0 in the horizontal vertical basis, or occasionally you have to send it in a mutually unbiased basis, diagonal. Okay? And what we have to do on the transmitter is just produce these optical states. And so we have this integrated optical circuit. Light comes in here, it's split. It is sent into this Mach-Zehnder interferometer, where the Mach-Zehnder interferometer allows us to send light into one of two possible channels on the output, this channel or that. And then there's an additional 2 phase modulators that allows us to change the relative phase of light in these 2 channels. The light then goes onto a square grating that you can see here, and depending on if the light hits this grating from the top or the bottom, it will emit from this grating in a horizontal or vertical polarization state. And if you send it in both top and bottom waveguide ports, you add horizontal plus vertical, which gives you diagonal. And if you apply a phase between the two, you get the other diagonal, 90-degree off from it. So basically, we can prepare optical qubits on a block sphere. And just to show you, here, for example, in this case, we decide we want to send either a horizontally polarized qubit or a vertically polarized qubit. And the isolation between the two states is pretty good, 30 to 40 decibels, which is sufficiently good for our needs. Okay? So then we used this integrated circuit, positioned it here in main campus at MIT, and sent polarization-based qubits over to Harvard. The problem when you do polarization-based QKD is in fiber, that fiber, because of its birefringence changing during the night and day cycles with temperature, means that your polarization state actually gets screwed up along the way. It's not actually fully screwed up, it's not scrambled, it's just modified in a way that you can pre-compensate. So what Bob here does for us is Bob sends back to Alice some information that allows Alice to pre-compensate the emitted state so that once it's gone through the fiber, it's been the polarization rotation through the fiber, the birefringence has been undone. And so Bob can faithfully discriminate between the different measurements. And so here what you see is the error that we have in our measurement with and without this polarization feedback on. The benefit of using polarization is that you use your resources at maximally well. The fiber has 2 spatial modes. If you want to squeeze the most information out of a fiber, you should use both spatial modes. Okay? And so here's the performance of this photonic integrated circuit-based QKD system. You see that with an attenuation of about 15 dB, we obtain in the intercity test some about 100 or so kilobit per second. In the laboratory, where the fiber is better stabilized and so on, we can get to about 1 megabit per second. So we're working now on improving that system. We think that we get something close to megabit per second now. So in the near future, we should be able to get maybe a megabit or a few megabit per second on one spectral channel, reaching sort of metropolitan scale distances. But the benefit, you wouldn't have much benefit if you just shrunk this one component out of your overall system and everything else remains large. The benefit really with the integrated optics approach, I think, is that you can pack a lot of devices in a small area. And what you see here is a chip developed with Michael Hochberg and Tom Baer-Jones at the time at OPSIS, a foundry for silicon photonics that contains 48 channels. So now you do the math. If we get a few megabit per second per channel, and using this, which is just, this is a chip that's a few millimeters on the side. Here you see the scale bar, that's a millimeter on the side here, 50 channels on that device. You can reach something like 100 megabit per second or so key rates in a metro scale network. Okay, so that would be about 2 orders of magnitude above the state of the art today. And that's sort of one of the things that's driving us in this direction. I want to come back to the Enigma machine for a moment, just as a side note. So when we look a little bit closer at this Enigma machine, what happens is you get a message that's a ciphertext. It's just scrambled. You punch it into these input keys. And if you trace through like an input key A here, it goes through and goes through all these different rotors, which reconnect the input keys to an output lamp. And then that gives you, the output lamp gives you what the unscrambled what the decrypted message actually is. And as we said, that thing was broken. Why? Because it was possible to intercept transmissions, and in that way make long logs of transmissions, and then figure out this, the settings of this Enigma machine. So the way to combat that problem is you should make messages that cannot be intercepted without them being noticed. And we actually implemented this protocol that was first proposed by Seth Lloyd of a quantum Enigma machine. Now our messages are photons. Our settings on this machine, rather than wires, are in our case, it's frequency dispersion. So we basically take a photon in and we apply to different frequency components of that photon. We apply different phases, different phase offsets. So we can stretch the photon, compress it, move it around a bit in time, and in this way scramble it. On Bob's side, he undoes that by having commensurate opposite dispersion and recovers the original message. And that has also got a security proof that's mentioned in this paper, and gives us now a quantum secure Enigma machine. Okay, but no matter what you do, whether you do these multi-channels or this quantum Enigma machine, if you only use photons in the way we described here, you will always be limited by losses in the fiber. So here is our records of QKD rates that show an obvious trend that the secure key rate, which is plotted here logarithmically, versus loss just scales really badly. And so, after with 50 dB of loss or so, just as a reference point, 20 dB of loss corresponds to 100 kilometers. So that's basically the end of metro scale when you go beyond it. So if you want to go outside the city, from city to city or so, you can't currently do that. And so what do we do there? So that's this idea, this really nice idea of a quantum repeater that was proposed first by Hans Briegel in 1998. And it goes like this, where you have this network again. And what you do is, between stations in the network, you produce some entanglement, let's say in whatever memory you like. It could be photons that maybe are stored well locally, or it could be some other form of memory like spins in a semiconductor. And if you, so Alice and Bob want to communicate, what they do is they produce, on this network, they produce pairwise entanglement between stations, okay? And whenever that happens, when you've entangled two stations, you know it, so it's heralded. So in this way, you can just go station by station until all links have been connected, and then you do this entanglement swap operation in the middle that connects the outer pairs of that link. And in this way, it's possible to distribute entanglement all the way from Alice to Bob by just breaking the problem into smaller segments. So one way you could do that is to use spins in solids connected to photons, as illustrated here. And so that's the second part of the talk. I want to go into how we're going about building these kind of networks. And so the choice for us at the moment is the Nitrogen Vacancy Center in Diamond. And this, a lot of pioneering work that you see down here at the slide showed that this NV center is actually a pretty good qubit. In the ground state, the NV center has a spin triplet configuration due to 2 electrons. And these can either pair against one another or pair alongside one another. If you put these two spins alongside one another, you pay an energy penalty to do the polar coupling of about 3 gigahertz or so. And so therefore, but as a position, if the spin is in state 1, but not if the state is spin 0, between a photon and the electron spin. So the photon that's then fluorescent from the NV is going to be entangled with the state of the electron spin. And the scheme there is then something like this. You repeat that spin-photon entanglement in at least 2 centers that are some distance of 2 electrons coupled, entangled with 2, the entanglement of 1. If you get up into refined coupling, people work in this regard to entangle time of the in a way so that we can kind of do the cavity part of the equation. What about the NV part of the equation? So the problem has been for us in the community that when you pattern around NVs, you disturb them because you create charge traps and things, and they can spectrally broaden the NV center. So it's no longer a very good emitter. And so we've put a lot of time into studying these NV cavity systems systematically. So where we then, we pattern alignment markers, QR codes, microscopic QR codes across the sample, then have a robotic microscope screen through hundreds of thousands of NVs, select good ones, and then we fabricate over pre-selected NV centers that have, at low temperature, characterized narrow line width. So here's just a snapshot. We haven't yet published on this because it's been quite a long effort, but here's a snapshot of sort of what things are looking like. You can see here this is the localization precision. So basically you take a diamond, put it in the microscope, it finds one out of, it finds NV center 55,762, right? You take it back out and you try to find the exact same NV center. You can find it to a pretty good precision of 30 nanometers or so, thanks to the integrated alignment markers. What is the distribution of line widths, of optical line widths of NVs before you fabricate over them? That's shown here. So when, by a number of steps, you can actually make the line width pretty narrow. Some of this work was, again, pioneered at Harvard. With line widths of NVs, at the resolution limit of some like 15 or so megahertz. So a good fraction at 15 or so megahertz line width. This is at 100 nanometers depth before you fabricate. Then the bad thing happens. You fabricate over these things, and the line width turn into this. This is actually sort of a good result for us, but it's not yet good enough. What you see here is a distribution of line widths. This is probability in terms of gigahertz. So the line widths shift. The line widths become much bigger, and afterwards, after this fabrication, you only have like maybe 8% of emitters with a line width below 1 gigahertz. So maybe 500 megahertz or so. So we're closing the gap on where we need to be, but we're not quite there yet. I'm hopeful. I think it will happen as we engineer these systems better and better, including in the SICM, that we can make good emitters that are reliably aligned to cavities. And if that happens, then then I think we're in the business. That would be, I think, the onset of this sort of like making that first transistor. Once you make that first transistor, you could really start scaling it. I'm going to skip over. Yeah. In this case, actually, these were implanted. Yeah, these were implanted. Yeah. So, it's not yet the end of the story. If you want to make a scalable system, you actually have to do error correction. That requires not one qubit; it requires a number, and it could be beneficial to create sort of small ensembles of NV centers to have enough qubits for error correction. And so, the idea is sort of illustrated here. We want to have maybe 4 NV centers, each of which has 3 carbon-13 nuclear spins, and they're close enough so that we can couple between NV centers electron spins, and in this way in total would have 4 times 3 or 12 data qubits, nuclear spin qubits. That's sort of like a parallel effort for us. We do this by implanting through small apertures in gold. You can see here a 10 nanometer aperture, and we can and here you see, for example, that in one aperture in this aperture, for example, we were able to see 2 NV centers with a distance of less than 20 nanometers. There's some straggle, even though if you go through a small hole, there's still a straggle. So we're continuing that, and the idea being that ultimately you want to have small, error-corrected logical qubits situated in each of these cavities, and then scale it up, Okay, so that's NV centers implanted through small apertures. Very quickly, there's, of course, this new kid on the block, the silicon vacancy center. And I just want to briefly talk about that. A lot of the pioneering work for that was also done at Harvard, but I wanted to point out that these other color centers that can be in metal alloys can actually be implanted using focused ion irradiation. And some of that work was done at Sandia National Lab. I just wanted to point out some work that we did in collaboration with the Lucan group on that. So here you see this is the source of silicon atoms that are accelerated, singly charged through this microscope, and then can be implanted with high precision of 50 nanometers or so into a photonic crystal, in this case a two-dimensional photonic crystal. And you can see actually the silicon vacancies, because of the symmetry of the ground state orbitals, is actually less sensitive to nearby electric fields, and therefore when you look at the line width of silicon vacancy centers implanted, first of all the ensemble line width of hundreds of silicon vacancies that we mapped out individually is actually quite good, of 50 or so gigahertz, but then individual ones can be close to 100 or so megahertz, which is close to the Fourier transform limit for the silicon vacancy center. So that's certainly a promising avenue alternative to the NV, although the spin states, you know, you remarked at the beginning that maybe we don't need dilution refrigerators. It turns out actually dilution refrigerators may be needed after all, sadly, to get very long coherence times in silicon vacancy centers, as was demonstrated by the Lucan group recently. Okay, so the thing is, suppose that somehow in the next couple of years we can manage to build our small logical qubits connected to cavities relatively well. You know, one immediate direction is going to be to try to build these distributed quantum networks for QKD and so forth. But can you do something else? There's a lot of interest in quantum computing. How would you build a quantum computer out of these small small repeaters? And so here's one architecture that we've been considering: is you tile a large number of atomic memories that you see here, NV centers for example, on a 2D checkerboard array, and then you entangle them pairwise with nearest neighbors by this heralded photon exchange. And as I'll show you in a bit, you know, and as we show in this paper here, this kind of a thing allows you to build very quickly a cluster state of entangled nuclear spins that then serves as a resource for one-way quantum computing. And so that's sort of the direction that we're going in on the quantum computing side, is trying to build this large cluster state. And so we have to assemble this kind of a circuit that has switches and has, you know, good memories and so forth. And the way we're doing that is, rather than trying to do everything in diamond, which for us is tedious and difficult, we try to fabricate the quantum memories only out of diamond, then position them into an underlying optical backbone that does all of the optical routing and the photo detection and so forth. So just a quick note on that. So the idea is to build sort of a quantum socket into which you can place your NV diamond. And here's an example. So in this case, actually, you can have just a diamond waveguide connected to a photonic crystal that's produced in aluminum nitride that also serves as a waveguide that then carries that photon away to the measurement region. And so we've done some of that assembly. We've placed diamond waveguides into photonic integrated circuits. Here's, you see an example. This is hybrid integration. This is a pre-selected waveguide with a good NV inside of it, and you can couple it very well to an underlying waveguide, in this case in silicon nitride. And you can do that repeatedly. We've assembled some, you know, in this case 4 of these good pre-selected NVs on one waveguide. So that basically allows you to cancel out the imperfect fabrication that you normally have. And here's a snapshot of where we are headed in this direction. Rather than using silicon nitride, which has significant autofluorescence, we now use aluminum nitride, which is a very wide bandgap 6 eV semiconductor that has very little autofluorescence and also electro-optic properties, Pockels cell effect. So we can make modulators. And also working with Carl Bergren's group, we've been able to integrate superconducting nanowire single photon detectors. So you kind of have the modulators and the switches and the photodetectors all in one platform, and hopefully that will allow us to connect these systems efficiently, also filters. All right, so so this is where we are. You see here just like this would be one circuit needed to entangle 4 NV centers. And we're kind of building up the technology to produce these pretty sophisticated chips. But we're guided in that effort, again, by our silicon photonics work. And I showed you earlier you know, our QKD silicon photonics work. Here's something that's basically that kind of a switch array, a number of optical switches that we're going to need to build for this NV system. And this has been actually a lot of fun in the silicon because again, the fabrication is so advanced. But you can see here that it's possible in principle. In this case, we have roughly 200 phase shifters individually controlled on an optical circuit. So that is possible, okay? Already now without too much effort. And it shows us that like this kind of a backbone that it's going to connect all of the spin qubits should be feasible. And just a side note, so this circuit was actually, it took a couple of years to develop. But I'm heartened that my students actually, some of my students in my group, and in the group of Marin Soljic, now use this circuit for a completely different application. It turns out it could be pretty promising for machine learning in deep neural networks, and have now started companies on this. Completely unexpected. When we launched into it, we had no idea it was going to be useful for this application. But when you do something very new, as all of you know, the unexpected things can happen. And it turns out it's actually maybe a pretty good interconnect circuit for deep learning neural networks. And my hope is that these guys are going to do a really fantastic job with that and are going to give us, sometime in the future, that chip with 1 million or so interferometers that we're going to need to build a decent modular quantum computer. Okay, so I've got my hopes up. All right, so just on the perspective, so for building these modular quantum computers, you would need this kind of large switch array with integrated, maybe hundreds or maybe even millions of quantum memories. But if you get there, you can really do some interesting things, including potentially error-corrected one-way quantum computing with these cluster states. And there's a reference on that, and I'd be happy to talk more about that offline. We've been doing a lot of other work also in the network aspect of things. How do you best, when you have an internet, 50 years ago, when not even that, some decades ago, when they built the first ARPANET, there were no protocols, right? So there's a lot of engineering had to go into how do you actually optimally route phone calls and then internet calls and so on. And similar efforts are going to have to be done on the quantum network side. And so we've been looking a little bit into how do you optimally distribute entanglement. It's a really interesting problem. All right. So with that, I come to a summary. So I've talked to you a bit about some of the efforts in the group on quantum communication. How can you speed up quantum communication using integrated optics and new protocols? And how can you extend it by the use of memories connected efficiently, hopefully soon, to spins? And if you have that transistor-like unit, then you can start doing some really cool stuff beyond quantum internet, where you can maybe make small supercomputer clusters, i.e. small modular quantum computers. So with that, again, my acknowledgments to the group members who've made this possible, to our collaborators, and thanks for your attention.
Very nice. Question?
What is the intuition behind the higher dimensional
Oh.
basically optimal use of vector Z prime and
Yeah, you got it.
otherwise you get linear communication.
Right. So, Christian, very, very good. Thanks for the very good question. So if you look at metropolitan scale distances in quantum key distribution, you can be limited in the channel capacity typically by 3 things. One is the error rate on the channel. That includes imperfections in your transmitter and your receiver. Dead time, exactly not dead time. It might be, for example, dark counts or so. It includes the source brightness, how many photons can you send per second, and it includes the detector saturation. Source brightness used to be an issue when people wanted to do QKD with single photons because you would only have such a bright source. But actually nowadays, we and others, use attenuated laser light together with decoy states, and that prevents, that pretty much solves the transmitter side of the equation. The problem still is on the detector side, where the detector can only click once every maybe 100 nanoseconds or so. So you get a photon, and then you just sit there twiddling your thumbs, not doing anything until the next photon arrives, which is very short in comparison. It can be 100 picoseconds for us. So the idea is you have a 100 nanosecond time span. You get a you know, you have a jitter on your detection of maybe 100 picoseconds, it's 1,000. So you could fit 1,000 slots in there. And that's exactly where actually these high-dimensional temporals, QKD schemes, can benefit you. Yeah, so thanks for the question.
I have a question about the deep neural net. Is your sigmoidal element?
Oh, yeah.
That,
Yeah, a very good question. That, for us, is a computer at the moment. So we actually, so we demonstrated the optical distribution part, but in that paper didn't yet implement the nonlinear neural response. And we are currently working on that exact problem. And I should mention that this is a close collaboration with a group of Marin Soljic, and we're taking a couple of different approaches to that, one of which could be to make use of nonlinear optical materials, saturable absorbers. They don't have to be coherent. They could be saturable absorbers. Another possibility that we have a tape out now is to just detect your photon on a photodetector and use a very short channel to drive a modulator. And if this, since that signal doesn't have to propagate very far, your losses of the high-speed electronic signals are negligibly small, and so we might be able to get around it that way. Super fast, exactly. Put the detector right next to the switch. Yeah, yeah, right.
Other questions?
Yep.
So how many units are currently engaged in your you already showed? Yeah, right here.
Oh, how many of these units do we have? Far fewer than we need. We have, so the most that we have assembled on one chip is 4. But I should say they're not yet entangled on one chip. The spectral stability is not yet good enough. It doesn't yet make sense. I mean, we could in principle place many, but they just wouldn't work well. So we're still working on the element. But I think here in the center, I think we have a very good chance in the near future to figure out that element reliably. And then it would be straightforward to place, I mean, in terms of area, you could place like 1 million or something on a centimeter squared chip. Yeah, yeah, right.